Hey physics friends, and welcome to 22.2, which is entitled Electrical Current. We're going to be getting away from what we've been talking about, which is static electricity, just electrons building up and then discharging instantaneously, with moving electrons over a period of time, and we call that electrical current. So we're going to talk today about something called Ohm's Law, and we're going to do a couple of example problems. You're going to also be introduced to different what are called schematic symbols. We're going to be building some circuits today, and we have special symbols for those. And we're going to get a couple of new equations, an equation for Ohm's Law and an equation for what's called power. So let's get started. So on my desk here, I've got some objects, things you probably are familiar with, maybe some things that you're not familiar with. So I've got a 9-volt battery. This is an electrical motor. I've got some what are called alligator clips. I've got a switch. I have a light bulb. And 3 what are called resistors. So let's just do a few experiments. So first of all, I can hook my battery right up to my light bulb, and you'll see that lights up. Now, I can hook up what's called a resistor. A resistor will limit how much current flows through my circuit. So now, I don't know if you can tell a difference there, but a little bit different. That was with 10 ohms. It's a unique unit of resistance, 10 ohms. I will do 68 ohms next and see if you can see a difference there. Can you tell? I'm really limiting how much electricity flows with these resistors. And then my last one, I'll do 820. A resistor is like a kink in the hose. The bigger the kink, 820 ohms, the less water can flow through my pipe. So now, all of a sudden, now I've got nothing. When I'm touching this, nothing whatsoever. So resistors are like a kink in the hose. I can line in a switch, and the switches are wired pretty interesting. You always have to use one of the middle posts. And I'll hook it up to my light. And then, when I flip my switch, I can turn the circuit on, and I can turn the circuit off. Now, I can replace this light bulb with a battery. This light bulb with a motor. So I can hook up an electric motor. Flip this on. Flip this off. On. Off. I can actually run it through a resistor. So I can hook it on and off by just touching these wires together to act as a switch. Or I can run it through a resistor. Might be hard for you to hear. Can you hear the difference? Running through a resistor limits the amount of current flowing through my circuit. So this is kind of built in real life. Let me take you over to a simulator so you can see a little bit more. Here I am over at my simulator, and I can simulate kind of the things that I was just doing. I'm going to drag in a battery. I've got a light bulb, and I'm going to bring in a couple of wires. So I'll just bring the wires in one by one to build a simple circuit. Now, circuits need 3 things to work. They need a voltage source, like a battery or a photocell or a capacitor. They need a conductive pathway. And in this case, these are wires. It could be a human being. You could be grabbing arms with somebody and electricity could flow through you because human beings are electrical conductors. The third thing you need is what's called a load. If you don't have a load, like I will get rid of this and I hook these together, you'll see that this is called a short circuit. Releases fire and smoke, and fun fact, electrical manufacturers always weave into their components little tiny bits of smoke so that if it short circuits, it releases its smoke and never ever works again. That's not true, but I did fool a few people with that in the past. Here's my light bulb. Now, I can insert a resistor. So I can cut this bring in a resistor, and you'll see that less current flows. And I can monitor the current by measuring it with this little device right here, and it will tell me 0.45 amps. I can get rid of that resistor, and now I have 0.90 amps. So I have more electricity flowing through here. Now, you're going to learn this in a little bit, but I'll tell you right now, voltage is like pressure, how hard it's pushing. So my battery, if I increase the pressure, meaning if I increase the voltage, you will see that I have more and more current flowing. Increase the voltage more and more current. Less pressure. If I push on the electrons with less and less, I have less current flowing. Resistance. We talked about that. Bring in my resistor here. So now I have less current. Now this resistance is like a pinch in the pipe. The more I pinch the pipe, the less water is going to flow through it. So I'm going to pinch this pipe more. So here I go, increasing my pinch. There's less current, and you can see it physically slowing down. This is a really great animation to kind of show this. I increase this. I can almost bring it to a standstill by having lots and lots of resistance. Or I can have a little bit of resistance, and you can see these colors are changing. Resistors have what's called a color code, and you'll learn how to read them later if you'd like, but I'll teach you how to read a resistor based on its colors. So I can have almost no resistance, a little bit of resistance. The more resistance I have, the less current. So these are what's called inverse relation. More resistance, less current. My voltage, on the other hand, is the opposite. More voltage, more current. Less voltage, less current. Oh, and then I've got a switch. I could wire a switch into here too. Open up my circuit. This is what we call an open circuit. If I put it together, this is called a closed circuit. Open up my circuit. Put in a switch. And switches make it easy to open and close a circuit. So here the switch is open. Now the switch is closed. I'm allowing current to flow through it. I can turn it off by disconnecting it. So this is an open circuit, closed circuit. Let's head back to our notes. Put a few things down. Circuits. What they are? Closed loops of current. They need three things. They need a voltage source. They need a conductive pathway. And they need a load, meaning some sort of resistance. A motor can be that resistance. The wire itself, like a heating element inside of a stove or a toaster, that could provide its own resistance. A light bulb, an LED, something needs to provide a resistance. If you skip the load, that's called a short circuit. You are short one of the three things, meaning that you are missing one of the three things. Skipping the load equals a short circuit. There's a few terms that I want to define with you. The first of these terms is called charge. It's just basically how many electrons. And we've been dealing with charge when we talk about static electricity. And we just count the number of electrons, and that's how much charge something has. The units for charge are coulombs. Voltage. These are all terms that you maybe hear: energy, power, voltage, current. How do you know the difference between them? Voltage is pressure. How hard electrons are pushed. Pressure. The units for voltage are volts. Current. Current is how many electrons are flowing per second. So it's different. Charge, there are 50 electrons on my microphone. That's charge. I have 50 electrons flowing every second past a point. That's current. Current is labeled in amps. Resistance. That's opposition to current flow. That's that pinch in the pipe that I had talked about before that resistors provide. The units for resistance are ohms. And it's this special, sometimes they're abbreviated with this, it's called an omega symbol. Looks like that. Energy. Energy is the ability to do work. Meaning that your ability to lift something, like to go against gravity. So electricity, we use it for work all the time. Energy is sometimes we call it the currency of the universe. Energy can neither be created nor destroyed. We're always taking chemical energy and turning it into mechanical energy or heat energy or light energy. The units for energy are joules. You'll learn a little bit more about those when we get into thermodynamics. And last, power. Power is how fast you can use energy. So it's the rate of energy flowing per second. The units are joules per second, or we made up an entirely new unit instead of joules per second. We call it a watt. Maybe you've heard of a watt in like stereo applications or something else along the lines. Maybe power supplies if you're into computers. How many watts? That's how much energy it can provide per second. Next, Ohm's law. This picture right here is a really good representation for what I like to call what Ohm's law. Ohm's law is this. It's simply written as V equals IR, where V stands for voltage. I stands for current. And R stands for resistance. So you can see here the pinch in the pipe. This ohm is squeezing that pipe, which doesn't allow the current to pass through. Voltage is pushing, how much pressure there is. So more pushing, more current. More squeezing, less current. So this little cartoon, as silly as it looks, is a really good representation for what Ohm's law actually is. Power. Power we can find, it's current times voltage, and power is also energy divided by time, where I represents current again, V represents voltage, E represents energy, and T represents time in seconds. So here's a couple of new equations for us in our tool bag. You've heard me talking about Ohm's law being like water. I've got a few things that you might recognize here. I've got 5 quote-unquote batteries. To be honest with you, this one is the only battery here. A battery is known as a collection of cells. And if you've ever taken apart a 9-volt battery, which you probably haven't done because you're good boys and girls, if you peel this apart with a needle nose pliers, there's actually 6 of these inside of it. Those 6 little tiny AAA batteries that when you add them all up equals 9 volts. Now, what's the difference between all of these? It turns out each of these has the same voltage. If you look really closely here, you'll see that it says 1.5 volts. If you look at a C battery, if you look really closely, it also says 1.5 volts. A AA battery, you look up here, says 1.5 volts. And on a AAA battery, it also is 1.5 volts. Each of these has the same pressure. But what's the difference then, Mr. Hare? The answer is how much water is in the tank. You probably had a super soaker before, like a squirt gun that you can pump up. Imagine a squirt gun that has a big tank. You could all pump them up to 20 psi. They all have the same pressure, but some of these just have a larger tank and they can supply water for a longer period of time. This is that water analogy that we're talking about. These all have the same pressure. A AAA, AA, C cell, and D cell battery all have the same pressure. Very different than what we call this, a 9-volt battery, because it has 9 volts. This has 6 times the pressure of a D cell battery, 6 times the pressure of a AAA. All of these have the same voltage except this one. And again, if you take one of these apart, you can peel this away, peel this open, and inside there is like a hot dog string of 6 of these. And 6 times 1.5 is 9, and that's where the 9-volt gets it from. It's just a string of 1.5-volt cells inside of it. So single-celled, these are single cells, and this is a battery because it has multiple. So with that water analogy, the more pressure you have, that's more voltage. The more pressure you have, you're going to have more water flowing. And then if you kink that with a resistor, you're going to have less in the end. The water analogy. I got a couple of example problems for you. We'll talk about what makes something have a little bit of resistance, and we're going to call it a day. So here's our first example problem. An electric motor. What's the power delivered to this motor? From before, remember that power is current times voltage. They're giving me the current, 0.050. They're giving me the voltage, 6.0. So 0.05 times 6 is, 0.5. So 0.5 times 6 is 3. The units for power are watts. So 3.0 watts. Part A. Part B. If the motor runs for 5 minutes, how much electrical energy is delivered? And you remember from before, power is equal to energy divided by time. So our power, 3.0 watts, how much energy? And remember that time needs to be in seconds. So 5 minutes, not going to work for us. 5 times 60 is going to be 300 seconds. And I'm just going to remember in my brain that I have 2 significant figures associated with it. So I'm going to take 3 times 300, and you get 900. Got to use 2 significant figures. Joules. So that's how much energy is being delivered over the course of 5 minutes. Resistance. What sort of things affect resistance when you have a wire? The longer a wire is, the more resistance that it has. Longer wires got way more resistance. A thinner wire has more resistance. A thicker wire is able to let more water flow through it, so same kind of holds here. Temperature. I mean, it's really cold out right now. When I'm filming this, it was negative 9 this morning when I woke up. The colder it is, the easier it is for electricity to flow through. Mr. Hare, why is it hard for my car to start? The colder it is, the harder it is on a battery. Cold is good for wires, but cold is bad for the batteries in your vehicles. The material. Copper. Copper is a really good conductor, and that's probably the most exclusive conductor that we use. Believe it or not, gold is a good, but we don't put gold inside of our houses and electronics. Sometimes we do in our electronics if we really need something specific. But all of the metals are conducting, some better than others. Next example. What's the current in this circuit? So we've got voltage, V. We've got resistance, R. And we're looking for the current, I. This is begging for Ohm's law. V equals IR. Where my voltage is 30. My current is unknown. But my resistance is 10. Ha! Insult to my intelligence here. 30 divided by 10 is just 3. Watch out for significant figures. 3.0 amps. And then lastly, schematic symbols. A lot of times on paper, we're going to write down a circuit, and we're going to use certain symbols to do that. Like, for instance, you saw me build a circuit like this on that simulator. If I was going to draw a schematic symbol, batteries are listed like this. And this is actually one cell right here. So if you have multiple cells together, the long one represents the positive end. So a lot of times people will label the positive and the negative. Here I've got a wire, so I just draw a wire. A switch looks like this, because that switch will close down and complete the circuit. We'll go up, and then we've got our light bulb, and a light bulb, the schematic symbol looks like this. And then we've got a resistor, and the resistor looks like that. Sometimes we label with how much they are, like maybe this is 10 ohms, maybe this is 9 volts. You can call this SW for switch, so sometimes switch number 1, switch number 2, and then light bulb. Maybe you've got multiple light bulbs, light bulb 1, but we put labels to certain things. All right, friends, I think I've rapped at you enough. You've been a great audience, and this is an introduction to Ohm's Law. Ohm's Law is probably the most important thing inside of anything electricity. Anybody who's in the electrical field will verify this, that this equation right here, V equals IR, dictates so many things in our world. All right, friends, talk to you later.